Hi, my name is Takumi Suzaki. I am a student at Hokkaido University, Department of Information Science and Technology. I'd like to present our paper, Expanding the Positioning Area for Acoustic Localization using Commercial Off-the-Shelf Mobile Devices. First, I would like to introduce the overview of our paper. I'm going to present indoor positioning technique for COTS devices using acoustic signal. We aim to expand the positioning area using proposed transmission scheme. Figure 1 on the right shows limited positioning area. I'm going to explain why it is limited later. Conducting experiments or proposed approach achieves high accuracy and a small variance compared to existing positioning techniques. Next, I'd like to explain the background. There are a lot of demand for indoor positioning. For example, navigation systems in museums, libraries, and shopping malls. In recent years, the pandemic has been widely spread. Therefore, it is important to manage the space, especially in hospitals. It is also important to monitor if enough distance is maintained. Another application is managing in the warehouse and logistics. It is expected to manage products efficiently. I'd like to introduce existing indoor positioning systems. One of the most famous systems is the GPS. However, signals do not reach indoors, so we cannot use them. Considering the applications explained in the previous slide, high accuracy, which is less than 20 centimeters, and low-cost infrastructure are required. Wi-Fi and Bluetooth systems are proposed recent years. However, they lack the positioning accuracy. Visible light positioning systems have been also proposed, but they do not work in a real environment. Ultra-wideband systems require additional hardware and are still not widely used. On the other hand, acoustic-based system achieves high accuracy and a low-cost infrastructure. In the acoustic-based positioning, we assume a user has a smartphone as a COTS device. From perspective of the smartphone, like figure 1, it is necessary to identify which speaker transmits which signal. In order to address this problem, most of acoustic-based systems adopt frequency division multiple access scheme because they have advantage of high positioning update rate. However, because they divide the frequency band in order to avoid collisions, they require a wider frequency band in total. We conducted a preliminary experiment for signal quality by angle and frequency shown in the figure 2. As you can see, angle and frequency increase, signal quality degrades, especially frequency upper than 14 kHz. This is the reason why the positioning area is limited using FDMA scheme. In the proposed transmission scheme, we use chirp signal, which is widely used in sonar and radar community. The equation expresses the chirp, and it has parameters of beginning frequency, end frequency, and the signal length. This chirp signal has characteristic of the frequency increasing linearly. In the paper, we propose FDMA and time division multiple access combined scheme. Figure 1 on the right is outline of the proposed scheme. There are multiple time slots and the speakers transmit low, mid, and high chops. Please make sure there's no overlapping bands in the same time slot. We designed this scheme aiming to mitigate the effect of frequency response explained in the previous slide. The first time slot with blank indicates the beginning of transmission, and all speakers do not send anything. Before moving to the next step, I need to explain about matched filtering. First, we make complex form of the chirp signal using the equation. Figure 1 is a simulation of the matched filtering. Figure on the top is transmitted chirp, and the figure in the middle is received signal with noise. As you can see the figure in the middle, it is difficult to detect the reception time. So we compute convolution using chirp and receiving signal. Figure in the bottom shows after matched filtering, and it contains clear peak. Finally, we select the maximum peak as the reception time. During conducting experiment, we noticed the reception time delays depending on the frequency. We conducted preliminary experiment like figure 1. Even though the distance between a speaker and a smartphone is the same, high-frequency signal result longer estimated distance. This delay is called group delay, caused by the microphone installed in the smartphone. Usually, sampling frequency of a smartphone is up to 48 kHz. So, there's a low-pass filter to cut upper than 24 kHz, considering the next rate. We are guessing this filter is causing the delay. Figure 2 on the right is actual measured delay in distance. It is clear that the delay increases as the frequency increases. We subtract this delay for calibration in this paper. In order to improve the positioning accuracy, we average receiving signals. In the averaging process, we perform coherent averaging. This is an averaging technique using phase information effectively. Figure 1 is the outline of the coherent averaging. After receiving high, mid, and low chirps, we perform matched filtering to obtain envelopes. Please make sure these envelopes include phase information. Finally, envelopes are added together to obtain the new envelope. Figure 2 is a simulation of the averaging. In the figure, incoherent indicates averaging without phase information. Coherent averaging achieves narrow main lobe, which results precise positioning because the location of the peak is strongly fixed. And finally, in order to estimate the position of the smartphone, we compute time difference of arrival. Here, xi, yi is position of the speaker. X, y is the position of the device. C is the speed of sound. Using these characters, we are able to make these two equations. With two equations and two unknowns, it is able to solve the equation and estimate the position. Figure 1 is envelope after averaging. We can detect reception times from speakers and then calculate the TDOA. In this slide, I'd like to explain the implementation. Figure 1 is experimental environment. First, signal generator makes chirps, and they are amplified. The amplifier and speakers are wired. There are 3 speakers transmit high, mid, and low chirps. We set 20 to 23 kHz chirp as high chirp, 16 to 18 kHz chirp as mid chirp, and 12 to 14 kHz chirp as low chirp. Speakers transmit these signals according to the proposed transmission scheme explained previous slide. We conducted positioning measurement at 14 positions, like in figure 2. We measured the true position using the Mach 3D system, which is an accurate motion capture system. Result 1 shows the performance of a proposed approach and the result of the delay calibration. Red points are estimated positions, and the blue arrow indicates mean of the estimated positions. The positioning error was almost the same, but proposed approach achieves small variance, this indicating stable peak after coherent averaging. Result 2 shows the performance of a proposed approach and incoherent averaging. As mentioned in the previous slide, incoherent indicates without the phase information. Proposed approach achieves smaller variance and a smaller positioning error. This result shows the proposed approach utilizes phase information to perform efficient averaging compared to the incoherent averaging. Result 3 shows the performance of a proposed approach and a single time third positioning. Proposed approach achieves smaller variance and a smaller error. This result clearly shows the effectiveness of the averaging and the transmission scheme we propose. Result 4 shows the performance of a proposed approach and FDMA-based positioning. Proposed approach achieves smaller variance and smaller positioning error. In FDMA-based positioning, center positions such as P5, P7, P8, and P9 achieve small positioning error because of the small angle and short distance to the speakers. However, other positions result large positioning error due to the frequency response. We investigated the reason why there is a large error in FDMA-based positioning. We made envelope of speaker right to P13 shown in figure 1. Figure 2 is an enlarged view of the signal from speaker right. As you can see the unstable envelope, this resulting wrong peak detection and resulting a large error. In our proposed approach, on the other hand, it is able to detect the clear peak, resulting small positioning error. In this paper, we propose TDMA plus FDMA combined schemes to mitigate the effect of the frequency response. Our proposed approach performs averaging outputs of matched filtering to improve positioning estimation. We also calibrate the delay in the reception time of high-frequency signals. Conducting a variety of experiments, we confirmed the robustness of our system and enabling large area positioning.